Hello, friends. Welcome. We shall continue our discussion. First, we will have a quick recap regarding the starting of three-phase induction motor. So, as it is the case with any other motor, even in the case of three-phase induction motor, the starting current is very high, normally called as starting in rush. We know already the reasons for this. Try to recollect the starting current very high in an electric motor and in the case of induction motor also, and this high current at the starting drawn will have the effects, and you remember we discussed the effects under two headings, local and then global. And local means what? It will affect if at all allowed to pass through the winding the winding might get burnt because this current is very high. Normally the windings will be rated for the rated current, will be designed for the rated current. This current will be many times more than the rated current. It has the local problem, and if you want to really make the motor capable of withstanding this, you will have to have the winding itself designed to take a higher current. Normally it doesn't carry that current, it's only at the starting, so economy becomes poor, the motor becomes unnecessarily very costly. That is the effect regarding the motor itself. Now coming to the other, that is global situation. That means apart from the motor, the effect of this high starting current on outside things. And what is this? The moment we draw very high current, what will it result in? It will result in dip in the voltage, poor voltage regulation. So that dip in the voltage, each time we start the motor, high starting current drawn, the supply voltage will dip, the line voltage will dip, and other utensils, other apparatus connected to this line, this supply system, they will experience a change in the voltage. Otherwise they should have been provided constant voltage. Now it will be a voltage which is changing in its magnitude. Obviously the performance of their apparatus will be poor. Hence it has a local problem and then a global problem. Hence there is a need to limit the starting current. IST needs to be limited, controlled. Okay, and what are the different methods of controlling the starting current? We have star delta starter, we have auto transformer starter, and then we have the soft start using solid state converters. Star delta starter is very simple, but it is in steps, only one change, whereas auto transformer starter is very good starter. You can change very smoothly, but very bulky, weight is more. Whereas come to this, using solid state switches, we can have the soft start using the converters, and because we are using power electronic devices, it's compact, it's light, and it can be smoothly started, because control we can have smooth control. Hence normally it is called a soft start. Okay, so there are different methods of controlling the starting current, and that's where we have different starters. Okay, now starting issues, the process of starting, when we think of, normally what all issues, parameters come into picture. How much is the time taken for starting is one parameter. How much is the energy loss during starting is another parameter, and then how much is the starting current is at another parameter. Like this, there are different parameters of interest associated with starting. Is it okay? Now these parameters will decide the starting mechanism that we choose, and the motor design that we select. Okay, so they have an effect. What type of motor I take, what type of starter I take, those things are decided by these parameters, the expected parameters. So starting is an important aspect in the case of an electric motor, and obviously in the case of three-phase induction motor also. Okay, so next we will look at the braking. So the braking in the case of three-phase induction motor, we have discussed braking in the case of DC motor. Now we will look at braking in the case of three-phase induction motor. So the braking, what it is, we know already. What is braking? Deceleration in simple, reduction in the speed, maybe leading to stop, okay. So the reduction in speed leading to stop may not lead to stop. Reduction in speed itself is called as braking. And what is the principle of braking? The principle of braking, can you recollect? Reducing the reason for motion. Something is moving, we want to reduce its speed. What we shall do? What is the reason for its motion? That reason, that cause itself will reduce. What is the reason for motion? The energy inside that system which is moving. So take out the energy within. That is one way of braking, taking out the energy within. The other way of braking is you create another force actively and counter the already moving system. This is head on. Take out the energy and counter it head on in the opposite direction with additional energy. Okay, that is the principle of braking. There are different approaches here, we know about these also. And in the case of electrical braking, we have these three methods. There is regenerative braking, there is reverse current braking, there is dynamic braking. And we shall look at these methods one by one in the case of the three-phase induction motor. So first we will take up the regenerative braking for three-phase induction motor. What is this regenerative braking? It is employing the principle that the energy stored in the moving system, that is the motor, is taken out so that it will decelerate. Part 1. Part 2, that energy stored is taken out but not wasted. Instead, it is converted into electrical energy and then fed back to the lines. That is why the name regenerative. We don't waste that stored energy. We take it out and feed it back. We retrieve that. We take it back. And what is the schematic? The schematic, here the stored energy in the motor, which is in the form of kinetic energy, is retrieved and fed back to mains. That is what we call as regeneration. That's what we call as regeneration. So the induction motor with its stator, with its rotor, stator field at a speed ns, rotor at a speed n, input 3-phase AC is the normal setup. And how we can realize regenerative braking? There are two approaches. One is A, as I have put here, it's with fixed frequency. When the supply frequency of this is fixed, then F is constant. Obviously Ns is constant. Why Ns is constant? Because Ns is equal to 120 F by P. When F is constant, Ns is also constant. And then N is less than Ns when it is motoring. And when I can make N more than Ns, it will be generating. N less than Ns, it is motoring. N more than Ns, it is generating. So here, if I can make N more than Ns, I can make this machine operate as generator. The stored energy is converted into electric energy that is fed back to the supply. That is with fixed frequency. But how do we make N more than Ns? That is possible only in the case of typical loads like gravity driven, wherein there is a possibility of speed becoming more. Otherwise, left to itself it will not become more. So gravity driven type of loads, there is a possibility of N becoming more than Ns. Hence, we can have regenerative braking. The motor acts as generator. Stored mechanical energy is converted to electric energy and fed back to supply. So here, when N becomes more than Ns, induction motor operates as induction generator. Operating point gets shifted to second quadrant. Operating point gets shifted to second. Earlier, when it is motoring, it will be in the first quadrant. Now when it is regenerating, it will get shifted to second quadrant. We look at that omega t characteristics. As the speed increases, the braking torque also increases. And as the speed increases, braking torque also increases. In the omega t characteristic, we have two regions. Look at omega t characteristic first, so that we will be able to appreciate that statement I made. Look at this. This is the omega t characteristics. Quadrant 1, machine is acting as motor, induction motor. This is the starting torque. This is the synchronous speed. Now, when we make the speed more than the synchronous speed, we get this characteristic. This characteristic is actually the generator characteristic, induction generator characteristic. So when the speed becomes more, I get this characteristic. And here you can see the torque is negative, which means the torque is braking torque. It's the opposing torque. And this opposing torque will be there as long as the speed is more than the synchronous speed. And this torque increases as the speed increases. This torque increases as the speed increases and reaches a maximum. This is the maximum braking torque. After that, still the speed increases, the torque decreases, the braking torque decreases. So look at that little carefully. As the speed increases, the braking torque increases. So when the speed increases, the braking torque increases, the opposition becomes more. Hence, that is the stable operation. But when the speed becomes more, if the braking torque becomes less, then obviously the speed again becomes more. We lose the control. That is why this portion is unstable. That is why I made the statement here, as the speed increases, braking torque increases for one portion. It is stable, and that is from omega ms to omega mx. Omega ms to omega mx. Whereas omega mx to above speeds, as the speed increases, braking torque decreases. That is why it is unstable operation. It is unstable operation. Look at this. So in this regenerative braking, omega ms to omega mx, it is stable operation. It is corresponding to the region from this to the maximum torque, braking torque. Are you able to appreciate that? So omega ms to omega mx, the range of speed for stable operation. The range of speed for stable operation. This is with fixed frequency. That means omega ms is remaining constant. If this is with fixed frequency, that is omega ms remaining constant. If the frequency is variable, then regenerative braking can be realized even for lower speeds. That is, how we can do that? By decreasing the frequency, I can make ns more, and if I make ns more, whatever actual speed I have, that speed can be made less than ns. That's interesting now. If I can make frequency itself less, ns itself will be less, whatever actual speed is there, that speed will become less than ns. To give the condition, no, it is more than ns. Whatever speed is there of the motor running, I can make that more than ns. by making ns less. Hence, the machine can be operated as generator and I can have the regeneration of the stored energy. This I told I can change the frequency. How? We can use a solid state converter and make the frequency variable. By having the frequency variable, we can have this condition realized, n more than ns. Is it okay? That's very interesting. What is that I am telling? See here, to have the regeneration, if the frequency is constant, I have to have the speed more, but that requires special loads. In the normal load, I cannot make the speed more. What I will do, whatever speed is there, for that speed I will make omega ms itself less, so that I will have this condition met. And a typical application of this is in the case of hair braking, no doubt, but it's also employed in the case of windmills. In the case of windmills, for generation, wind energy generation, even when the speed of the windmill decreases, when the speed of the wind decreases, windmill speed also decreases. We will be able to generate the energy even at lesser speeds if we can have this type of thing. Is it okay? Okay. Then this method, the regenerative braking, the merits: more economy, efficiency is more because energy we are not wasting, and heating is less because energy is not lost in the rotor, it's taken. No temperature rise issues, and it is suitable for large machines because when the machines are very large, regenerative method seems to be the only method because the dissipation of heat poses a very big problem. And the disadvantage, it is complicated, and the condition n less than ns is to be met. That's why it becomes complicated. That condition is to be met. Is it okay? Otherwise, regenerative method is a very good method, no doubt about it. Loss of energy we can avoid, and the efficiency becomes more, economy will be better, and no temperature rise issues, no temperature rise issues, but control needs to be little done properly. It is complicated. So based on this, we'll take a problem. Look at this problem. A 440 volts star connected 3 phase 6 pole 50 hertz induction motor, it's a 3 phase induction motor, has the following equivalent circuit parameters referred to stator. R1 is 0.1, R2 is 0.08, X1 and then X2 both are equal, 0.2 ohm. Assuming the motor is braked by regenerative braking, determine the maximum overhauling torque which it can hold, the maximum braking torque, the speed at which it will hold a load with a torque corresponding to 50% of what has been determined, that is 50% of the maximum. Try to read the problem, try to figure out how you can proceed. You can proceed yourself, no doubt about it. Just try to figure out how you can proceed. Is it okay? Just try. I will give a pause here. Just try. We'll have a small pause for you to try. Take a pen and paper. Try to figure out how you can proceed. Sorry. Read the problem. Try to feel the problem first. This is pause for you to try. Don't fast forward. Take a few minutes. Try on your own. Try on your own. Then you can compare with the solution that I am going to give. Are you trying? Good. Good. Some of you have started. That's good. Doesn't matter even if you go wrong, but try. That's very important. Because the way you think when given a problem is very important. You can correct yourself if that is wrong, otherwise you can feel very happy that you too can think in the right direction. 2 minutes more. Take that pause, please try. Good. No need to get the actual values, you can just sketch out the approach, how you can go ahead, what is given, what is asked, what all equations you can use, just the steps approximately. 1 minute more, just another minute. It's a pause for you to try. Yeah, continue. You can expect the numericals of this type here. Okay, right, we will look at the problem. You please compare what you have done with this. The first thing is what this problem is about. Let us be clear. So this problem is asking this, there is regenerative braking. This is first quadrant, this is second quadrant. Regenerative braking, the characteristic will be this, and this is the maximum braking torque, and this is the speed omega ms. This is the speed corresponding to maximum torque, and the slip corresponding that is sm. What is asked is how much is this torque minus T max, number one. Number two, what is the speed at which the braking torque will become half of this? Very simple, na? The clarity of what is asked is very important. Okay. Now, the given equivalent circuit per phase, approximate V phase, 0.1 RS, 0.2 XS, 0.2 XS, look the, and then X2 0.2, RS 0.08 divided by S, divided by S, 0.08 divided by S, that is the equivalent circuit. Now how much is V phase? V phase is 440 by root 3, 254. And this torque maximum braking happens at this slip, and the expression for that slip we know already. It is thus, I use that expression, substitute and get that, and Sm I get as 0.194 plus minus both. However, we know that the minus sign is taken for regenerative braking. That is why this Sm is minus 0.194. Once I find that the slip, then ns 120 f by p 1000 rpm, omega ms 2 pi ns by 60 104.7 radians per second, and T maximum equation 3 by omega ms ir dash square r2 dash divided by sm, and ir dash, that equivalent circuit, V phase divided by impedance, resistance part, reactance part, simplify, we will get 501.9 amperes. And look here, this slip is with minus sign, that's very important. This slip is with minus sign. Okay, and that current 501.9 I will use in the expression for T max. What I will get, 3 by this omega ms, ir dash this value, and then R2 dash by SM 0.08 by SM, that is minus 0.194. When I simplify, I will get 2976.4 Newton meters. Then the second part, 50% of this torque is minus 1488. When we will get that, what is the speed corresponding to that? I will use the expression for torque. In that I will substitute this torque. Unknown is S, otherwise everything else we know, and S I will find, and this becomes a little involved mathematically. That equation when we solve, we get S either as minus 0.059 or 0.62, but 0.059 we cannot take, it corresponds to motoring, very small value. 0.6 no, it corresponds to this 0.059 is a very small value. It corresponds to 0.62 corresponds to very high value. It corresponds to, because SM how much we got, 0.194. If this is 0.194, more than this 0.194 will come somewhere here. This region is unstable region. That is why this 0.62 what we are getting, it is unstable region. We don't take that. Therefore 0.059 minus is the one we select. It corresponds to less than 0.194, that is the operating point falls here. This is a stable operation. So we get the S as this. After substituting this S in the expression for n equal to 1 minus S into ns, but S is minus, we will get 1050 rpm. So the 50% of braking torque we will get at 1050 rpm. 1050 rpm. 1050 rpm, ns is 1000, slightly more than this, somewhere here we will get half the maximum braking torque. Is it okay? So in this whole thing we understood the problem, and more important, we drew this characteristic. That made our understanding very clear. And then we went to the equivalent circuit, and the equations we used, then it was very smooth equations we used. Only thing is we got to two values. Resolving, we went back to omega t characteristics and then resolved it. Now I will give one more problem for your homework. Please try it yourself. Take this problem. A 440 volts star connected 3-phase 6-pole induction motor has the following parameters. Refer to stator. RS RR dash 1 ohm, XS XR dash 2 ohms. For regenerative braking, determine A, maximum overhauling torque it can hold and the range of speed, safe speed operation. B, speed at which it will hold an overhauling load with a torque of 100 Newton meters. It's almost like the earlier problem, slightly different. Okay, please try to solve it yourself. I will give this as homework. Please try yourself. Okay, so we shall stop there. Next class we will continue our discussion. Bye. Take care.